Okay, energy. What we're going to be talking about, hopefully, is work. How is energy related to work? Okay, another thing we're going to be talking about is all the different kinds of energy. Kinetic energy, potential energy. But within there, we're going to be talking about electrical energy. We will talk briefly about chemical potential energy, chemical kinetic energy, all kinds of spring potential energy and stuff like that. We'll be talking about power. Not the power that you guys have over me or I have over you, but I mean, how much time does it take to do a specific amount of work? That type of power. We'll talk about how energy is conserved, how you cannot create or destroy energy. It can only become some kind of other energy. Simple machines like a pendulum, like a ramp, like a lever. Mechanical advantage. When you are using a simple machine, you still do the same amount of work. But remember with the pendulum we have up on the board? We had to pull twice as much rope, but we only had to apply half as much force. That's a mechanical advantage. How many of you can pick up an engine out of a car? Not many. However, using a simple machine called a pulley, you would be able to. You'd be able to apply enough force to lift it. You may have to pull a lot of chain, a long distance of chain, but you can still do it. Would like you to talk at your tables. Are there any words here that you do not know what they mean? Talk. Not sneeze, talk.
Bless you.
Bless you. Five, 4, 3, 2, 1. Okay, you guys know what a seesaw is?
Yes.
Okay, a seesaw is a type of lever. This little thing down here that it goes over is called the fulcrum. Okay, you can have the fulcrum different distances from the sides. Did you guys also know that there are some places where teeter-totters or seesaws are no longer allowed? They're too dangerous. Okay, my brother, you remember my brother I was talking about? Okay, the mean one that tried to show me what frictionless ice is. Okay, what he did is he's 7 years older. He's about twice as heavy as I was. And he would get on the teeter-totter on one side. I'd be on the other. And he just, I'd go flying through the air. Or he would get off the other side, push it down, and then let me, poof! Yeah, but no kidding, that hurt. And so some people have sued city parks for teeter-totters or merry-go-rounds. Oh. Another one that people have trouble with is the joule. Joule is just like newtons. Newtons are the unit for force, correct? Joules are the units for work and energy. Okay, and we'll talk more about that in a little bit. Radiant energy is the energy of something that radiates, like the sun. Okay, are there any other things that you guys did not understand? Okay, yes. Okay, which one? This portion of the teeter-totter is the arm. How long is the arm of the lever? the length of the arm. They sometimes call it that. Okay. May I go on? Okay. Now, there are different forms of energy. Kinetic energy is the energy of motion. Rotational kinetic energy is the energy while something is rotating. It's a different type. We're not going to talk about it a lot. I just want you to know about it. Gravitational potential energy is dependent on gravity, but it means it has a potential to do work or to transform into another energy. For example, if I take this baseball, I hold it up in the air. It has a certain amount of gravitational potential energy, potential to do something. If I let go of it, it becomes kinetic energy. It's transformed into kinetic energy. Elastic potential energy. Remember when we did the spring lap and we stretched them out? The more they stretched and did not break, the more potential energy they had. So when you let go of them, it would go up and down. Transform into kinetic, elastic kinetic energy. Chemical potential energy is, remember you ate earlier today? That's what's making you tired right now? Because what happened is the chemical bonds in your food are chemical potential energy. Your body breaks them down, lowers, and then it goes in, the sugars go into your body. Your body releases insulin, drops your sugar levels. That's why you're tired right now. Because your sugar levels actually are below where they should be because you ate too much sugar at lunch. They will go back to normal a little bit later because of a chemical called glucagon. And so the chemicals are allowing you to interact. Your body breaks down your food, breaks down the chemical bonds, the chemical potential energy, and makes ATP. You use that ATP to think, to breathe, all kinds of things that the chemicals allow you to do. Electrical energy, we'll learn more about that when we get to the electric circuits. Light, duh. Sound is the energy. Remember when we were dropping the egg drop devices and they hit the ground, you heard a sound? That was actually beneficial because some of the potential energy was transformed into sound energy, making the crash not so bad. It was not a heck of a lot, but it did. Or thermal energy is what happens when you touch the top of a stove. Don't do that. Okay? Any questions on any of this? You have a question?
Oh, me?
Yeah.
No.
Okay.
Oh, I had a question before, but no, I don't.
Okay, thank you.
No, it's okay.
No, go ahead.
No, it's okay. It was a stupid question.
There's no such thing as a stupid question. Ask it anyway.
When you're saying that when you eat, it makes you tired. If you don't eat, will you not be tired?
Okay. No, what I'm saying... Okay, if you eat too much sugar, what's going to happen is that's going to get into your body. Your body's going to break it down, and it's going to shoot your sugar way, way up. That's why during fourth period, you guys are nuts. You're bouncing.
As I have math.
Okay. Okay. After lunch, you guys are generally nuts. Then, what happens is your body says, I can't do that. That's going to damage my cells of my body because I have too much sugar. And therefore, it's going to release a chemical called insulin that's going to decrease the amount of sugar in your bloodstream. When it reduces that, it overdoes it. And that's what's happening somewhere between end of fifth period and now, is your sugar levels are too low. If, on the other hand, you ate something like vegetables and meat, that wouldn't happen. Okay, vegetables and nuts or some other protein. That sugar crash would not happen. Okay. Kinetic energy. Kinetic energy is the energy of motion. That is the equation up on the board. I might ask on a test, what does this equation tell you? What happens to the kinetic energy as you have more and more mass? Does it increase or decrease? As you have more mass going a certain speed, what happens to your kinetic energy? It increases. What happens for the same car if you're going twice as fast? You have more kinetic energy. Question? Now, the interesting and scary part of that is that little number beside the V. That little number besides the V makes it scary because if you're driving in the car, the faster you go, it becomes much, much more dangerous exponentially. I'll explain that in a few minutes. It also means, remember the Newton cradle? The thing where you have those little balls hanging down, and you pull one out, and you release it, and one goes out the other side. From what we learned up until today, we could take two balls from one side, release it, it hits with a certain velocity. We know that two go out the other side with the same velocity. But according to momentum, two go down here, one could go up here with twice the speed. It would still be the same momentum. But according to kinetic energy, that's not possible. And you will never see that with a Newton's cradle. It's always going to be 1 and 1, 2 and 2, and so forth. Okay? So, kinetic energy is dependent on mass and speed. It's proportional to mass. If you take a little bunny running at 1 meter per second and you double its mass, it's going to have twice as much kinetic energy. Double the mass, double the kinetic energy. However, if you take the same bunny and you scare it, oh, poor bunny, and instead of running at 1 meter per second, it's running at 2 meters per second, it's got 4 times as much kinetic energy. Questions? May I go on? Or do I need to wait a second?
Can you go back?
There? So, if you are driving, okay, I'm going to do the math for you, so you don't need to basically do anything here. If you've got a 1,000 kilogram car, okay, remember the formula is ½ mv squared. If I take half of 1,000, that's 500. Multiplied by 20 squared is going to give me 200,000 joules. Okay, you don't have to do the math. If, on the other hand, I take the same car and I'm going 40 meters per second, what happens is I quadruple the amount of kinetic energy. Then, if I triple the speed from the original, I increase the amount of kinetic energy by 9-fold. A side point. Anyone have questions on that? a side point on this. If I go from 0 to 70 meters per second versus going from 70 to 100 meters per second, which one requires more energy? Going from 70 to 100. Why? Because we start out with the velocity squared already high. And we go to one that's humongous squared. And so it's almost exactly the same amount of energy, a little bit more, to go from 70 to 100 than from 0 to 70. Okay. Now, so what? So, if you're going at the initial speed and you want to brake, okay, you see that bunny running across the street. Okay. You apply your brakes. The brakes apply a force of 700 newtons. Well, the brakes apply a force of 700 newtons, and they have to work to slow you down. When they do that, work is equal to force times distance. And so this 200,000 joules is equal to the force of 700 newtons times some distance. And that distance happens to be 28 meters. Anyone have questions? Then, if we do the same thing for the next faster car, going at 40 meters per second, it now takes 4 times as far to stop. Bye-bye, bunny. And then, instead of doubling the speed, you quadruple the speed. It takes you 9 times as long to stop. But if we talk besides just the physics, if you're going 20 miles an hour, you see something in front of you. You have a reaction time, say of 1 second. During that 1 second, you go a certain distance. If you're going twice as far, and you have a reaction time of 1 second, you're going twice as far, and so forth. Any questions? So you've got not only the braking, because your kinetic energy, but you've got your reaction time. Yeah.
In The Incredibles, there's a scene where Mr. Incredible stops the train. Would that be possible?
No. Well, if he stops the train in a short distance, the problem is there'd be a huge amount of force in a short amount of time. What happens to all the people inside the train that are not attached to seatbelts in that short amount of time? Their momentum, their inertia is going to keep them going, and they're all going to land up in the front of each car. Okay, so it's possible if he applies enough force, but everyone in the train's going to die. Maybe that's why they got sued. Okay, I know too much of the show for most teachers. This is just showing you what I said graphically. Okay, a short distance at 30 miles per hour, much farther for 60, and much farther still for 90. Please think twice about getting in a car with someone that drives too fast. Because if they drive too fast, I want you to be here for your 10 and 20 year reunion. Okay, enough with kinetic energy, potential energy. Potential energy means it has potential. Gravitational means it has to do with something with gravity. How high it is, its vertical position. The potential energy is basically called stored energy. It has potential to do something, generally potential to move. Okay? May I go on? Okay, so the equation for potential energy. And again, I have no idea why it's called U. I typically on a test will call it PE. It's not physical education, but potential energy is equal to mass times gravity times height. That means if you increase an object's mass, its potential energy goes up. If I take this baseball versus just shot put, which one's going to have more potential energy 2 meters above the ground? Shot put, because it has more mass. G. For G, if I take this baseball 1 meter, 2 meters above the ground on Earth, on the moon, or on Jupiter, will they have the same amount of potential energy? No. Why? Because G is different on the 3 locations. Yeah.
What about like the shape of the object? What if it's like a different shape?
Doesn't matter. For potential energy, it doesn't matter what the shape is. It's the mass. The third thing is how high is it? And here it's a little bit tricky. If I take this baseball and put it on the table, okay, right here, does it have potential energy? Sort of. In relationship to the top of the table, it has 0 potential energy. If I drop it from the top of the table, will it fall to the top of the table? No. In relationship to the ground, does it have potential energy? It has a positive potential energy. Compared to my hand, which is about 2 meters above the ground, does that ball on the table have potential energy?
Yes.
It has negative potential energy. Why? Because I have to add energy to get it up here. I have to work to bring it up here. Therefore, down here, it has negative potential energy. Questions? The more mass it has, the stronger the gravitational the field, or the higher it is up, the more potential energy it will have. Questions? Yeah, go on. Okay, I just talked about this with reference point. How do I get energy? How do I get energy is by working. Okay, I can give something potential energy. I can give something kinetic energy by working on it. I can push something. I remember when I had my chair out here and I was pushing whomever, I gave them kinetic energy. If I take this chair and pick it up, I give it potential energy. If I feel tired afterwards, that means I've been working. Yeah.
Does like a car have potential energy?
Okay, a car, yes and no. Okay, the gasoline in the car has chemical potential energy. When we break those bonds, the potential energy goes into kinetic energy by the exploding gas molecules pushed down on the piston. And that causes the wheels to turn. That turning there causes kinetic energy on the wheels, and so forth. Machines make work easier. You do the same amount of work, but you have to apply less force. When you apply less force, you have to do it over a greater distance. That means if we look at the equation, work equals force times distance, we can write that force times distance multiple ways. We can say force times distance, or force times distance. We can have these two be equal to each other if we use a machine. Lift a motor out of a car It's kind of hard for us to do with our arms. But with a pulley system, where we pull a lot of chain, we can lift with a much lower amount of force. Work is also over a longer distance, unlike last unit. Remember when we were talking about impulse? There we changed the time. We could have a huge force with a small time, or a small force with a large time. Here we can have a large force with a small distance, or a small force with a large distance. Same basic concept. And the unit for work, the unit for energy is called the joule. The unit for work is force times distance. Force is newtons, distance is meters. How that became joule, I don't know why. Maybe because energy is so valuable. And back 300-400 years ago in the time of Newton, joules were very valuable. Diamonds, emeralds, rubies. Yeah, not the tiny kite. If I push something for 1 meter, I do 1 joule of work. If I push this object right here and it doesn't move, am I doing any work on this object? No, because it's not moving in the direction I'm pushing it. Or I come over here and I lift this chair. If I lift this chair against gravity, I'm working right now. Okay? But right now, when I'm holding it, am I working on the chair? No. I may be applying a force to keep it up in the air, but I'm not moving it up and down. Therefore, I'm not changing its potential energy. I could walk around all day with my hands on it, and I'm not working on the chair. Questions? Does that make sense? Because I am not changing its distance up and down. Yeah. It's a change in potential energy. It's a change in chemical energy, in kinetic energy. If I remember when people were sitting in the chair, I had to apply a force over a distance to give you to start moving. Okay? Or I had to work to slow you down. Brakes have to work to slow you down. What the heck? Work has a specific meaning. It's a measurable change in a system. So in order to work, if I'm pushing on a brick wall, I may be doing a lot of force on the wall, but unless the wall moves, I am not working on the wall. Did you hear that last part? I am not working on the wall. Inside my muscles, they may be working. Little twitches back and forth. But I am not working on the wall. May I go on?
Monday.
Power. Okay, I know it's still Monday. Power means if I'm doing some work, how much time does it take? If we look, if I take my Fiat, I go from 0 to 60 meters per second. That's a certain amount of change in work. But it may take 3 minutes. If I take a Dodge Charger, and it takes 8.2 seconds. If I divide by 8.2 versus 180, this power is going to be much bigger with the Dodge Charger. So it's the amount of work divided by the amount of time. Now, just like Newton, just like joules, there is a specific name for power. What is the unit for power? What are the units for power? Exactly. Watts are the unit for power. I was telling you all along. Except it's W-A-T-T. When you do something, it does not matter, when you're working, it does not matter how you get there. Going up that hill, I am working going up the hill. If I go straight up, I do the same amount of work if I have to use hairpin turns going up the whole thing. Power is simply in watts. Some places you may have heard of horsepower. That's what we use for cars in the United States. In Great Britain, they use British thermal units for power. There are different types of power based on where it is. You do not need to know this. This is extra. We can also conserve energy. If I take this baseball, I can make it change. I can add energy to it. When I add energy to it, I work on it. I increase the number of joules in it by working on it. If I add a certain number of joules and I put it at a certain height, I have done a certain amount of work. It has now a certain amount of potential energy. Up here, it may be 100% potential energy. How much kinetic energy does it have right now? 0. I let go of this. Right before it hits the ground. It's now down to 0 potential energy, 100% kinetic energy. Questions? To repeat that, if I take it at all the way up here, it's 100%. All the way down, it's 0% potential. Where is it the potential energy equal to the kinetic energy? Halfway down. If it's 2 meters, it's 100% potential, 0% kinetic. At the 0, it's 100% kinetic, 0 potential. At 1 meter, it will be equal to each other. Now, we can transform. You do not need to write this down. If we take a sledgehammer that has a mass of 100 kilograms, it will have 980 joules of energy, of potential energy. If you're holding it up there, it has 0 joules of kinetic energy. I drop that down right before it hits the nail. It has 0 joules of potential and 980 joules of kinetic. Can it work? Can it do work? When it does work, how much of that, all that work, all that kinetic energy is going to go into work, and it's going to force the nail down a certain distance. Questions? Now, what's amazing is, I've got about 5 minutes. Please listen. If I take the equation, I'm going to go on a roller coaster. This is at the top of a roller coaster. This is at the bottom. I have potential energy, mgh, plus 1/2 mv squared kinetic. At the very top, it's all potential, no kinetic. You know that split second where you're not moving? Where you freak out? Yes. Yeah. At the very bottom of the first drop in Goliath, what is it, 3.5, 4 seconds later, you have no potential. You're all kinetic. Has your mass changed whatsoever? Besides maybe getting sick to your stomach? No. So what happens is that means that you can divide everything by mass. What does that mean? That means that for a roller coaster, listen carefully. It doesn't matter whether you're on the cart with all the preschool kids or all the old farts that are from Dieting Club America. Okay? you will be going the same velocity at the bottom of that loop, whether you're with the small kids or whether you're with Dieters Anonymous. Okay? Now, this right here, I'm not going to show it right now because you don't have any time. On my website, remember I showed you the ones that had to do with Hewitt? Or if you have access to this, I would highly suggest you watch it. He does an excellent job of, almost as good as I do, explaining this stuff. And it's available to you 24 hours a day. So if you need something to put you to sleep, it might be beneficial.